Hello, today we'll be looking at translating a polar equation to parametric equations. After watching this video, you should be able to translate a given polar equation, where r is a function of theta, to parametric equations, and find the equation of the tangent line to a curve expressed using a polar equation, where r is a function of theta, for a given value of theta. Alright, so the first thing we're going to do is we're going to find parametric equations corresponding to the polar equation here, r equals 1 plus cosine theta. Now really the sort of the backbone of all this here is this set of equations, right? So if I'm given a point in polar coordinates r theta, then I can convert it to Cartesian form using these equations. So this is what we're going to do here, in fact. So you'll see here that r is 1 plus cosine theta, so I'm going to put that in for both of these r's. And let's just distribute and rewrite it as cosine plus cosine squared and sine plus sine cosine. Now we don't have t here, but theta is also a fine variable, and so we can leave this here as our parametric equations. Alright, so now that we have our curve expressed in parametric equations, we can now find equations for tangent lines. So let's actually find an equation in Cartesian form for the line tangent to the curve r equals 1 plus cosine theta for the given value theta equals pi over 4. Alright, so first let's take partial derivatives here. So I'm going to take dx d theta. Alright, so the derivative of cosine is negative sine. And here I have to use chain rule, so that's 2 cosine theta times the derivative of the inside, which here is negative sine. I can rewrite this now as negative sine minus 2 sine cosine. Alright, now let's look at dy d theta. You have to use the product rule. So first times the derivative of the second plus second times the derivative of the first. So this is minus sine squared plus cosine squared. So now let's write, so in general, dy dx is the dy d theta divided by dx d theta. Cosine, I mean. Now I want the slope, though, at this particular point, theta equals pi over 4, so let's evaluate. So cosine of pi over 4 is root 2 over 2 minus root 2 over 2 squared plus root 2 over 2 squared Alright, so let's do a little bit of simplification here. Actually, I might go to the next page. So if I square root 2 over 2, that's 2 over 4, plus 2 over 4. And this is going to be All right, now let's simplify a little bit more here. So the 2 over 4s, and this I can rewrite as all right, so there we have the slope of the tangent line. So this is the slope of the tangent line. Okay, now we want to find the particular point which on the curve. So let's consider the equations that we had, right? So x was cosine of theta plus cosine squared of theta. So at theta equals pi over 4, this is root 2 over 2 plus root 2 over 2 squared. 2 over 4, which is 1/2, so root 2 plus 1 over 2. And let's check for y. Right, so that's what we had for y. Now I plug in theta equals pi over 4. Root 2 over 2 plus root 2 over 2 times root 2 over 2. So again, we have root 2 over 2 plus 2 over 4, which simplifies to root 2 plus 1 over 2. So this is the point. And again, this is in Cartesian form. So the point on the curve is, maybe we can write it as 1 plus root 2 over 2. All right, so there's the point. We have the slope, so we can use point slope form. So the line is so it's y minus the y coordinate, and it equals, I have the slope. So the slope of our tangent line was, we'll have to look up here. So remember, it was negative root 2 over root 2 plus 2. And then x minus the point. So there's the line expressed in point slope form. Next, we'll check this out using some graphing technology. All right, so let's double check our findings here with Desmos.com. First, we see the graph of the polar equation r equals 1 plus cosine theta. For the point corresponding to theta equals pi over 4, we found it to be 1 plus square root of 2 all divided by 2 for the x component, and the y component is the same, 1 plus square root of 2 divided by 2. And here we see our point slope form for the equation of the tangent line in Cartesian coordinates. And as we see right here, it looks like a tangent line. Right? If we get really, really close to the point, we'll see that eventually the polar curve itself is almost indistinguishable from the tangent line. Well, I hope you found this helpful.